Welcome to the third lecture. So let's start with some recap what we did yesterday. So we start by sharing the screen. Okay. So let's start with some recap of what we did yesterday. So yesterday we stopped by saying that, well, not we stopped, we started actually the lecture yesterday by saying that differential equations naturally give you iterated integrals, and we started looking at the simplest class, which are these multiple polylogs. And I remind you the definition. They're defined recursively because they're iterated integrals. And then the same function with one indexless. So it's a recursive definition that contains in particular the log a is not 0, why when a is 0, this is just defined to be log x. And it also contains functions like the die logarithm as special cases. So that's the definition of multiple polylogs that we looked at. And then we started discussing some properties. So the first is there's the weight, which is the number of integrations. And then we said that they form a shuffle algebra. Meaning that, for example, well, if you take two polylogs which have the same upper integration limit x, then their product is obtained by this idea that you have two decks of cards and you sum over all the possible ways of shuffling these two decks of cards. So here the two decks would be A, and the other deck would be the deck BC with B on top of C. Okay. And this generalizes in the obvious way, and the result is called the shuffle algebra. So then we also, well, since now we know that this is since we now know that polylogs form an algebra, we introduced some notation. So we defined AN to be the vector space of all polylogs of weight n. So I'm allowed to take linear combinations of polylogs that have the same weight. And the scalars in my vector space, so the coefficients of the linear combination, are rational numbers. Weight 0 objects are the rational numbers. Again, I remind you that you can replace rational by algebraic everywhere without changing anything. And we said that this algebra A that I get by putting all of these vector spaces of polylogs of different weights together is a graded algebra in the sense that if you multiply together a polylog of weight m and a polylog of weight n, you get a polylog of weight m plus n. So the weight is preserved in this procedure. And then we also started to look at the other structure, which is a Hopf algebra. So now I have, maybe let me also remind you what a Hopf algebra is, or say co-algebra first. A co-algebra is a vector space together with a map that allows you to take one vector and returns a pair of vectors. And this map is called delta, which is called the co-product. And in particular, it is co-associative, which means that if you iterate this map, which allows you to split things into two. If you iterate it so that you can split things into three, it doesn't matter how you iterate it, if you iterate it in the left vector or in the right vector. And we looked at an example of such Hopf algebra, and what we took was, well, words made out of letters, or equivalently decks of cards. And the multiplication is the shuffle product, just like the decks of cards, and the co-product is deconcatenation. It is summing up all possible ways of splitting a given deck of cards. And we argued that that gives a Hopf algebra. And for example, we checked that this compatibility condition between co-product and product holds, that if you multiply together two decks of cards using the shuffle product and then you split them, it's the same as splitting the two decks and multiplying them individually. So that is where we stopped yesterday. Are there questions about what we saw yesterday in the lecture? So far, this idea of Hopf algebra is not yet connected to polylogs. This will come later. But are there questions just about the mathematical setup? No? Okay. Let's go on. So we've seen now that there's this shuffle algebra. If you take these decks of cards, you can shuffle them. That gives you a Hopf algebra. But we also know that polylogs form a Hopf algebra. And actually, you can show that polylogs form a shuffle algebra, and you can actually show that they also form a Hopf algebra. Now, the co-product is a bit more complicated than the one that was just the concatenation. And we'll come back to that later. And I'm not going to give you the complete definition of the co-product or how to compute it here in the lecture, because it gets pretty involved. It becomes very technical, but it is very algorithmic. You can just do it easily with a computer. Rather than giving you the general formula, let me discuss some examples. So, for example, what is the co-product of a logarithm? So that is the co-product of an object of weight 1. Well, if you take a log, which is an object of weight 1, how can you decompose into simpler pieces? Well, it has weight 1, so you would not expect that you can break it into anything simpler. So you only get nothing in the first slot, which means 1, answer the log, or you put the function in the first slot and nothing in the second. So that is the way that the co-product will act on a log, on an object of weight 1. Now, how does it act on objects of weight 2? Well, first you can check how it acts on a product of two logs. Now, this you can get because you know that the co-product must satisfy this relation. So just by using that relation and repeating exactly the same calculation that we did yesterday, you can see that the following identity holds. And one thing that I just want to highlight is that you have here this product, which is clearly symmetric in the two factors because multiplication is commutative. And what you see here is that, well, you have these two trivial terms that you always have, always two ways of decomposing an object or splitting it into an object is always not to split it, so that one of the two factors is empty. And then the only non-trivial part that you have here is log x tensor log y plus log y tensor log x. So it's symmetric in x and y because the original object log x times log y had this symmetry as well. Okay, it's pretty obvious, but it's good to highlight it. So two comments here. One is that you always have these trivial terms, which are shown in yellow. One tensor the whole object tensor 1. Then the rest is the non-trivial piece, which in this case is symmetric in the two factors because it came from a product. So how would it act on a dialog, which is also an object of weight 2. Again, you have these two trivial factors. You always have them. And then the only non-trivial factor here is the one in the middle. And that one, you see, it's not symmetric anymore in the two factors. Why? Because the dialog does not come from a product of two logarithms. Now, why is it this particular log 1 minus x tends to log x? There you would need to go to the general theory and you can derive it, but that is what comes out. More generally, on the classical polylogs, with x like this is there, you have an easy and simple formula. So again, you always have this trivial piece, and then you have the rest. Again, why this particular form? You would need to go to the general theory, but we'll also later on will motivate why this and why not, for example, the other way around. Why not for the dialog? Why is it 1 minus x, x, and not x, 1 minus x? This will motivate a bit later. For now, accept it. These are the formulas that you get. Okay. So now let's do the following. So we start from this formula for the co-product of the classical polylog. And let's make an exercise. Let's just say, okay, this is an identity. Oh, it was the definition, if you like. That is how my co-product will act. And this should hold, of course, for every value of x. So in particular, I should be able to put x equal to 1. But if x is equal to 1, remember that we've seen yesterday, you know it, that the ln evaluated at 1 is zeta n. It's the Riemann zeta function evaluated at n. So those are numbers that you get very often. This is a special case of something I guess you may be more familiar with, which is that Li2 of 1 is pi square over 6, which is when pi square over 6 is zeta 2. So let me also put x equals 1 in the right-hand factor. So the first term, of course, then put x equal to 1 and I get just, well, I place Li n by zeta n. And the same for the second factor. In the third factor, you can see that, well, because of this log x in here, if we put x equal to 1 there, I find 0. Except if k is equal to 0. But k is never 0 in this sum. So this last term for x equal to 1 will always vanish. So putting it all together, I conclude that if the above formula is true, then the formula below should also be true. Good. And now well, this is something that we just remind you in case you don't know. So zeta, whenever you take zeta 2n, you evaluate the zeta function as an even integer, this will be proportional to pi to the power 2n. For example, zeta 2 will be proportional to pi squared, zeta pi squared over 6. Zeta 4 is proportional to pi to the 4, it's pi 4 over 90, and continues like that. In particular, you see that zeta 4 is actually proportional to zeta 2 squared. Okay, so that's a relation that we know holds. Just because whenever you evaluate the zeta, the Riemann zeta function, an even integer, it will be proportional to pi to the power 2n. Okay. But what does that mean? Well, that means that clearly, if I act with the coproduct on each side of this relation, then, well, what happens? Well, first of all, delta is linear. with respect to rational numbers, because the rational numbers were a scalar, so I can pull out this factor 2 divided by 5. And I can also pull out this 2, because, so this 2 I can pull it out because delta of A times B is delta of A times delta of B. And so if A is equal to B, then I get that delta of A squared is delta of A squared. Okay. And so, well, let's go and just push the argument to the end. If you expand this out, then you get that delta of zeta 4. Well, there are these two trivial terms that you always get. And then you have this guy. But that's now a problem, because you see, I have now a contradiction. Depending on how I computed delta of zeta 4, either starting from the formula in the very first line and putting x equal to 1 and n equal to 4, or start with, if I start from the first line and put x equal to 1 and n equal to 4, I get this with n equal to 4. While if I start from here, I get this. So I get an additional term. So something is not correct in this reasoning, clearly, because depending on what I do, I get different answers. The only way to reconcile the two things is that I say the second term is somehow 0. So zeta 2 tensor zeta 2 is actually 0. Now there are two ways you can go about it. And again, what I'm going to do now is not a mathematically rigorous treatment. I'm just going to give you the flavor. We can also, for those who are interested, we can discuss what the mathematical meaning is. So zeta 2 is pi squared over 6. So I should somehow put pi to 0. Because I will put pi to 0, then of clearly zeta 2 tensor zeta 2 will be 0. Now, of course, you can say, what does it mean to put pi to 0? But you can also see that it's enough that I put it to 0 in one of the two factors, either the left or the right. For example, if I put zeta 2 to 0 in the second factor, then I'm fine. The price I have to pay is that delta of zeta 2 will now be zeta 2 tensor 1. Delta of zeta 4 will be zeta 4 tensor 1. Or in general, delta of pi will be pi tensor 1. And that is what you have to do. Again, this is not the mathematically rigorous derivation here. I just showed you. If you don't do it, you run into trouble. And the solution is that you need the special treatment for pi. Why the special treatment for pi, and why do you keep it in the first factor but not in the second? This will motivate later. It's related to the question why was the dialog 1 minus x, x, and not x, 1 minus x. There's a symmetry built in that we haven't explained yet. Okay, other questions?
Yeah, let me ask one question. Is it only pi? In other words, if you put 1/2, for instance, in Li2, then I think there's a log term, a log of a pure number.
It's log 2, 1/2 log 2 square plus a term proportional to pi square, yes.
Yeah, something like that. So if you went through the same exercise, would the log 2s behave properly, or?
Yes, they do. And actually that's a very interesting thing. So maybe let me, to illustrate how deep this goes, let's maybe go through this example in detail because it's very instructive.
Okay.
It's a very good comment. So let's make a little exercise. So let's go and take lead 2 of 1/2. Okay. Well, and let's go and take the formula that we have here. That's the formula for a computer core product of V2. We go to a better place. I just want to copy it so that I can put it on the other slide. And we can look at it. So that is the general formula. Let me just keep it here so we can look at it. Oops. Why is it so big? I don't know. Okay. Let me just write it down. So delta of lead 2 of x, the general formula is 1 tensor lead 2 of x plus lead 2 of x tensor 1. And let me introduce a notation which is often very useful, which is that I say it's delta prime of lead 2 of x. Because you see, there are always these two trivial terms which do not carry a lot of information. So the only information is in the remaining terms. So it's enough that I look at this thing called delta prime for all practical purposes. And that for the dialog is log 1 minus x tensor log x. Good. So let's put x equal to minus 1, x equal to 1/2. What do I get? Well, I get the delta of lead 2 over 1/2 is equal to delta prime minus log of 1/2 tensor log of 1/2, which is minus log 2 tensor log 2. Each log of 1/2 gives me minus log 2. I have two of them, so nothing changes. And you can easily check that this is actually the same as the delta prime of minus 1/2 log square 2. So what you conclude is you get that lead 2 of 1/2 is minus 1/2 log square 2 plus something, plus a number, which must be such that it is killed by this delta prime. Now, I'm just telling you that that means that C is actually proportional to pi squared. And indeed, delta of pi squared is pi squared tensor 1. So it only has this trivial term, so its delta prime is 0. So what you conclude is, you conclude that lead 2 over 1/2 is minus 1/2 log square 2 plus some multiple k of pi squared. This multiple you have to compute it numerically. There's just no other way. It's like an integration constant. But you know that that is the general structure. Okay, but the interesting thing comes now if you go on, actually. And then let me do that because it tells you, well, it shows you what is actually happening here. If you evaluate it numerically, let me quickly do it. You find that k is 1 over 12. But let's go on. Let's then look at lead 3 of 1/2. You can use the general formula. You can, and then you plug in all the numbers. You actually get this. You would need to go to the formulas that I showed you before. That's what comes out. And what do you get? Well, you get actually, well, let me first, look here, this is this. So I can plug that in. I get minus 1/2 log squared 2 plus pi squared over 12 log 2. And I should change the sign because log 1/2 is minus log 2 plus log 2 tensor log squared 2. And there's a 1/2 which came from here. Okay. Well, I can rewrite this a little bit. And what I get is I get this. I get minus log squared 2 with the factor of 1/2 tensor log 2 minus pi squared over 12 log 2 minus 1/2 log 2 tensor log squared 2. Okay, so what do I, and if you play a little bit with it, you would see that this comes from, actually, comes from delta prime of minus 1/6 log cube 2. That would give you precisely these two terms. And then there's this one term left. Well, and this one term that is left comes from minus pi squared over 12 log 2. And note that in order to do that, it was important that, I mean, pi square only, you see, there's an asymmetry built in. In order to go back, I needed already the asymmetry. Because if well, if you go through it, you see that this identity holds. So what you conclude is, you conclude that Li 3 of 1/2 is equal to minus 1/6 log cube 2 minus pi squared over 12 log 2 plus a constant that vanishes when I act with delta prime. And here I have to tell you that there are two of them. Which are these two. Actually, if you want to be pi, always comes as I pi, so let's put an I. You would find that C2 is equal to 0. So that's the integration constant. You have to do it numerically. There's no other way. And Mathematica. No, apparently Mathematica tells me that somewhere a sign mistake. Apparently it is like this. I would need to check where I did the sign mistake, but that's not important. And this is 7/8. Fine. Okay. So you've also found what Li 3/2 is. Now the interesting thing comes if you go to the next layer, if you go to Li 4. Let me go through that because that is very instructive. So let's go on. Now we know this procedure. We go here, and if I do it, plus Li 2 of 1/2 tensor log of 1/2 squared divided by 2 minus log of 1/2 tensor log cube of 1/2 divided by 3 factorial 6. Good. And now I can plug in what I know. And now something very interesting happens. So I plug in the expressions that I had already for Li 3 and for Li 2. It will be a bit long, so I'm not going to write it explicitly. The only thing I want to highlight is the following. There will be a term that will look like this. where does it come from? Well, it comes from there is a Lie 3. And the Lie 3, we just said, it can write in terms of log 2s and pi squares and the zeta 3. And then there are other things which just have pi squares and log 2s. Now, the interesting piece is this. Why is it interesting? Because what I would like to do is I would like to say, but this comes from this, right? That's what I would like to do if I want to continue the game that I've played so far. But this doesn't work because if I evaluate this, then since zeta 3 is not proportional to pi square, it would give me both terms. And this one is the one I have, but I get one more. The consequence of this is there's no way I can go back. So while it is true that Lie 2 is minus 1/2 log 2 square plus pi square over 12, then there's this formula for Lie 3/2 that has a term that is log cube 2, a term that is log 2 times pi squared and the zeta 3 for some coefficients. This fails here. And the reason is precisely that pi square had this asymmetry while zeta 3 did not. So you see, it's to answer your question, you said, well, does the same problem arise for the other constants? No, it's even the other way around. It's precisely because you have this asymmetry in pi that you get for these, you get these reduction formulas in the first place, but they fail in general and you get these new transcendental constants. That is actually how the whole machinery will be set up. You will be able to derive identities of this type in this way, but you will need to use the fact that pi has this special role.
It wasn't obvious that pi squared was the only constant that was going to have this asymmetry, but I guess you're telling me that by assuming that, the rest is consistent.
Yeah, and well, we will come back to that, but let me tell you why pi is special. It's actually, when you think about it, it's rather obvious. What is I pi? I pi is the discontinuity of the log. So the reason that pi becomes special is because you have multivaluedness, and the multivaluedness is precisely what is encoded in I pi. And what you need to account for is that you somehow need to correct for the fact that things were multivalued, that you have discontinuities, which is precisely what is captured by pi. And everything else are just constants that have nothing to do with things being multivalued. That's what it will boil down to. We'll see that in a second. That is why it's only pi that has this problem. Okay?
Yeah, thanks.
Good. So, yeah, there's more like a technical interlude. Well, let's jump over it. I think with the lecture it's not important. Well, no, just use it for the language. There is a difference between something called a coaction and a coproduct, which is precisely related to this asymmetry. I will here for the lecture just use the two words interchangeably, coaction, coproduct, and I will just use this special definition for pi. Yeah, so now comes precisely what is related to that, which is what is the meaning of the two entries? And that will also be related to the question. Let's first look at the following. Before we answer this question, let's play a little exercise. Let's first differentiate a function and then compute its coaction. So I first differentiate, then I do its coaction. Good. Differentiating the dialog. Well, the dialog has an integral representation. I remind you what it is. the dialog, remember, is defined like this. And so you can see that the derivative of the dialog is just minus 1 over x times the log. Okay, this is here. So I evaluate this, this derivative. Now, minus 1 over x is a rational number. Say if x is a rational number, so minus 1 over x will be a rational number, or in general, it's a rational function. And we said that rational objects are the scalars in our vector space, and delta is linear, so I can pull it out. But log 1 minus x, we know what it is, we computed it. And so, well, that's what I get. And now let's compare it to the following. I now go and I first compute the co-product of the dialog. And then I do the following operation, which I denote by this, which means that this means act with ddx only in second entry. Because I act with ID, the identity in the first entry, and with the derivative in the second. So I only act in the second entry. What do I get? Well, I know how to evaluate the co-product dialog, and I act with the derivative in the second entry always. Clearly, the derivative of 1 is 0. The derivative of the log is 1 over x. And the derivative of the dialog is what we had already here. And what you see is you get the same thing. If you take into account that 1 over x is a scalar, and so you can pull it out of everything. So, and this actually is not an accident. The following identity holds. Derivatives only act in the second entry. So the second entries encode the way the function behaves under differentiation. So differentiating a function and then taking its co-product is the same as computing the co-product and then only computing derivatives in the second entry. So the second entries encode the behavior under differentiation, or they encode differential equation, if you like. Now, what about the first entries? Those encode discontinuities. So computing a discontinuity of a function across a branch cut, and then computing the co-product is the same as computing the discontinuity only in the first entries. And then this connects to the discussion we had before. You see that, I mean, the discontinuity of the log is 2 pi I. But since you only should compute discontinuities in the second factor, you would only ever get that as, so only ever in the first factor, you would only ever produce factors of I pi in the first factor, never in the second, because it's only the first entry that encodes discontinuities, not the second. That is, if you want, another way of understanding why pi has this special role. It's because what the co-product encodes is in the first entry the discontinuities, in the second entry is the derivatives. And I pi's are related to discontinuities. Good. Yeah. Right. Let's skip over this, I guess. Well, we can maybe go through it if you like, what a discontinuity actually is, but I think, at least for most people, it's, you understand the idea. So maybe let's jump over this. And let's just, well, let me just tell you that the discontinuity of the dialog has a branch cut which starts at 1 and goes all the way to infinity. And if you cross this cut, the value of the function jumps by 2 pi I times the logarithm of x. If you compute the co-product on both sides, what you get is, well, you get this. You just compute the co-product of each factor. The co-product of 2 pi I is 2 pi I tensor 1. The co-product of log is 1 tensor log x plus log x tensor 1. And then you multiply them back together, and you get these two terms. And you see, you only get I pi, well, in the first entry, which is the same as what you would have gotten if you had computed the discontinuities only in the first entry. Where now, clearly, the discontinuity of 1 is 0. The discontinuity of 2 pi I log, you get it from here, which is this term. And the discontinuity of log is 2 pi I. And so again, you see that you get the same thing. That's an example. Are there questions? So this is the meaning of the two entries in the co-product.
Just quickly, for the logs, you put the cut starting at -1 going to minus infinity?
Yeah, so I was indeed a bit sloppy how I put the cuts. They are from 0. So here, the discontinuity of the log would be on the negative real axis, which means that for log 1 minus x goes from 1.
Yes, I meant the negative real axis. Sorry. Yeah. Okay.
In the end, that was the part that I jumped over. We can also go through it if people want. In the end, it's immaterial because whatever way you put it, it wouldn't matter because you can interpret it as going around the singularity. And it wouldn't matter how you put it in the end, as long as you do it consistently. Yeah, I didn't want to go into details of how to define discontinuities unless people want to. More questions? Okay, so if there are no more questions, I guess we can go for coffee, and then we start in 15 minutes, and then we look at examples of what you can do with it. So far, we've only looked at the definitions of what is algebra is. In the next lecture, we will actually apply it and do computations with it. And therefore, I think this is a good place to have the coffee break and restart at 11.
Can I ask something?
Yeah, sure.
Where are we headed? So don't want you to give everything away, but I mean, what's the drive of? I mean, I understand we're learning lots of properties about these iterated integrals, and can you maybe just in a very few sentences say how this will help you to calculate more complicated processes or more higher order processes or something?
So this is the mathematical language that you need to speak if you want to evaluate these things. So if you do a two-loop calculation, you will get gazillions of these functions. So you have to somehow handle them.
Understand how to reshape them into something.
Yeah. We'll come to that now. But the question will be, how can you reshape them? Maybe get more compact expressions, get expressions that are easier to evaluate numerically. So this is the, well, if you want, this is the equivalent of, remember when you were a high school student, you were doing exercises with trigonometric functions. You had these tables of like identities for sines and cosines and all of these things.
Yes.
This is the equivalent of that. So this is the machinery that you need to use if you actually want to do calculations.
Okay.
If you just use the basic things that you learn in textbooks in Pascal and Schröder, it's not going to help you. So because the mathematical language that you get for higher orders is much more complicated. You get these additional functions.
Okay, thanks. That's fine. That's good enough.
Okay. Okay, more questions? No? Okay, then let's start again. So, yeah, maybe to pick it up from what we just discussed. So when you do these multi-loop calculations, you get gazillions of these functions. We started trying to find the basis for these integrals that you need to evaluate, and you said you can use differential equations to evaluate them, which leads to these iterated integrals, which then lead to these functions. So what we're doing now is figuring out how we can manipulate these functions. For example, one question you can ask is, yeah, you got 20 pages of polylogs, can you maybe compactify them? Maybe if you can compactify 20 pages into half a page, your numerical code will run faster, for example. Now, all that goes under the name of, well, goes under the umbrella of finding relations among these functions. That's always what it boils down to. Whatever you do, it boils down to finding relations among these functions.
Okay, and the Hopf algebra structure helps you to find them.
Yeah, we'll do exercises now to figure that out, well, how that works. It takes some time to get there because you need the language, but we'll now look at examples. Now, the last thing we need is a conjecture. That is actually the core of the whole thing. That is actually something that is a very strong mathematical conjecture. It comes from mathematicians, not from physicists. So we introduce this notion of weight, this number of integrations. And the conjecture is that there is no relation whatsoever that relates MPLs that have different weights. That means, for example, you will never be able to write a dialog as a logarithm. Maybe a product of logarithm, but not a single logarithm. Just to give you some background of the math, we had defined the space A, the vector space of all polylogs, as a direct sum of these ANs, which are the spaces corresponding to polylogs of a given weight n. The fact that the sum is direct is, well, this conjecture is reflected in here by the fact that the sum is direct. Remember, direct sum, you can think of it as vector spaces that are orthogonal to each other, so they don't talk to each other. So by saying that this sum is direct, I am saying that there's no way that a polylog of weight 2 will talk to a polylog of weight 1. And this is what will guide us. So this notion of weight is a very robust thing, and you can just not relate things that have different weights. So let's take an example. Let's take the example of imagine you have done a loop computation and you get this expression here, P, which is dialog 1 minus x plus the product of two logs. So it's two terms. And you ask yourself, can I somehow simplify it? Of course, well, it's a bit academic because I have two terms, but this is meant to be an example. So to set the scene, you can say, okay, I have computed my loop amplitude and I got two terms. Can I somehow simplify this expression? And let me do the following. Well, let me compute a co-product. Then let me, for now, this thing is the same as what I called before, delta prime t. The 1, 1 down here just refers to the fact that I look at terms in the co-product that have functions of weight 1 in the first interval. So what will happen? What will happen is the following. So the dialog so that's what we called before delta prime. It's the same in this case here, this is the same thing. Would be this. And so you see that if you take the dialog of 1 minus x, you get the same formula as here, except that you have to replace x by 1 minus x. So this comes from here. The product of two logs, well, we've said that that gives you the symmetric sum of the two terms. And now, what you see is immediately that there's actually cancellation of two terms. So this term clearly will cancel against this term. And only one of these three terms survives. But if you compare that to this, you see this is the same thing, up to a sign. So this actually is the same as what we would have gotten from a single dialog up to a sign. So you can conclude that the thing you started from, which is this, is actually the same as this single term. Well, at least when you act on it with a co-product. Now, can you say the arguments of delta 1, 1 are equal? No, they are only equal up to terms that lie in the kernel of this linear map. The kernel, well, the kernel contains many things, in particular in practice, for all practical purposes, what lies in the kernel is always the zeta values. It's not the only things that live in there, but pretty much. For all practical purposes, that's what it is. So it means that the green identity here is true up to the zeta value, but since there are no relations among objects of different weights, the only zeta value that you could have is zeta 2. So that is something like an integration constant. You cannot get it from other considerations. You need to look at numerical values or look at the value at some point. In particular, put, for example, x equal to 0. If x is equal to 0, then, well, this here becomes zeta 2. Log 1 minus x gives you 0. And 0 times log x is still 0. And on the other side, you have this, which is at x equals 0 gives you 0. So if you can add a constant to it, it must be zeta 2. And so you find, for example, that this relation holds. So you manage to write your result of your calculation, which are two terms, as just one term and a constant. Now, this is a bit an academic example, but it shows you the kind of things you can do. You can manipulate your expressions. Now, why do you care about these relations? Well, that is something that we said before. Well, for example, imagine you computed something that is 17 pages of polylogs. But actually, that's the first time this technique was applied. You actually realize that these 17 pages can be compactified into one line. And of course, if you need to study or if you need to evaluate one line, that is much more efficient than if you have to do it for an expression that is 17 pages long. And there's no way you would figure out how to do that without a mathematical structure that guides you. You just try things at random, applying identities here and there, that wouldn't work. The upshot is that all these relations among these functions are essentially guided and governed by an algebraic structure, which you can exploit in your calculation. So exploiting can mean, as I said, like simplifying complicated expression. It may also mean optimizing your results for numerical evaluation, because remember, these functions have branch cuts, and evaluating functions that have branch cuts is always an issue. But you may, for example, manage to rewrite it such that in each region of the parameter space, the functions admit a fast convergent series representation. Okay. So that is why you care about these relations. Maybe at this point, it would be good to do some exercises just to show you a bit how these calculations can be done. In particular, how to how to use it to derive relations. So that's what I would propose to do. And we will do that in real time because it's easier to follow. For example, one thing that always comes up is when you look at these functions ln of x, we said already they have a branch cut starting at 1. There's infinity, here would be 0. And they admit a convergent series representation in the disk around 1. So this function admits a series representation of this type. So whenever x is less than 1, you can use the series representation to evaluate this function. If x is greater than 1, or an absolute value greater than 1, so here you need x less than 1, how could you evaluate this function? Well, there are ways to relate this function to that function. Now, how can you find this relation?
Did you mean k to the n there?
Oh, yeah, sorry. Yeah, thanks. Yes, like this. Thanks. So how can you, for example, find this relation? Now, of course, again, this is a bit of an academic exercise because those relations for these Lien functions are known. But you should imagine that this would be not Ln, but some G, and the procedure they're going to show you will work the same way. But expressions are long that you can only do by computer. You cannot do it with well, a pen and paper anymore. Okay, so to get a feeling, let's first look at n equals 1. E1 of x. And let's do it the other way around. Let me express E1 of 1 over x as Ln of x. So I want to write this as E1 of x. Well, E1 of x is actually minus log of 1 minus 1 over x. And so what I can do is I can write this, for example, as log 1 minus x plus log minus x. So the log I know, I don't need anything special. And what do I do, for example? Imagine, well, just to be concrete, let me fix x is, for example, between 0 and 1, just to be concrete. Now, then, of course, this thing here is negative. This is between 0 and 1. And this thing here is negative. So what do I do with this? This is the log of a negative 1. And that is the problem also here. This thing here has a real and imaginary part. And I somehow want to find a way to write it as something where the real sphere expansion. So what do I do with this guy here? Well, the only way forward is to fix a branch for the log. For example, fix log minus x, be log x, and let's choose minus I prime, for example. You can also choose plus I pi if you want to work the same way. So if you do that, you will see that E1 over x is equal to E1 of x, which is this guy here, plus log x minus I pi. So that is the analytic continuation of E1 of x. When x lies between 0 and 1. Okay, that was easy. I haven't done anything special, just massaged it a bit. But that I could easily do because it's just a log. Weight 1, everything is log, everything is easy. Let's look at n equals 2. So I want to write 2 of 1 over x in terms of V2 of x and possibly this much. And I'm still working with my assumptions that x lies between 0 and 1, and that I fixed the branch of the log such that this holds. This was my convention. Okay, so what can I do? Well, at first glance, not much because it's a new function. So the best I can do is I can compute its co-product. Let me use the notation 1, 1. So I need to compute the co-product of this guy, pulling out all the terms in the co-product that have 2 factors of weight. So let's give me log minus 1 over x, tensor log. Now for this guy, I can use the formula we had on the previous slide, which was that this is log minus log 1 minus x minus log minus x So here for the yellow, I have inserted the formula that we had here. And I expand it out. And I get this. Now, what do I find? Well, this, you can easily compare it to what we had here. You will see that this is equal to delta 1, 1 minus V2 of x. This, you can see, is delta 1, 1 of 1/2 log square x. And this, sorry, this color isn't very visible, it's orange. This should be the same as, now you have to remember that there's this asymmetry for I pi, comes from here. So what do you find? Yeah, you find that this is the same as the image of minus V2 of x minus 1/2 log square x plus I pi log x. So you found that delta 1, 1 of V2 of 1 over x is the same as delta 1, 1 of this expression. Where now V2 of x when x is between 0 and 1 well defined, and also log x when x lies between 0 and 1 is well defined. So what you conclude? Well, you conclude that V2 of 1 over x is equal to minus V2 of x minus 1/2 log square x plus I pi log x plus a constant. We said these constants must be zeta values. And we had weight 2, so it can only be a multiple of zeta 2. Well, which multiple? Well, put, for example, x equal to 1. Then the left-hand side becomes V2 of 1, which is zeta 2, equals to minus V2 of 1, which is zeta 2, minus 0 plus c times zeta 2. So you find that c must be equal to 2. And so you found this relation between dialogues. So you can now, whenever you have a dialogue where you have an argument 1 over x, say, which would be a real number greater than 1, you can replace it by this combination with c equals to 2, and you can evaluate it. And the imaginary part would just be this, because everything else is real. And now I hope you can see how you go on from here. What happens is you just go through recursively. For example, if you take n equals 3, let's just do this one. Now, how would you go about this? How can you relate these guys? Well, let me first, this guy, delta 111 means that I use the co-product to decompose my object into triplets. And then I take all the terms that have a weight 1 object in each entry, so a log in each entry. You would have to go through the calculation using the formulas that I gave you, and you would find this. Which I can also write as minus log 1 minus x tensor log x. So log x minus plus log minus x, so x minus I pi tensor log x tensor log x. Again, I just used the formula that we had for how to rewrite log of 1 minus 1 over x. Let me spell it out. 1 minus x tensor log x tensor log x plus log x tensor log x tensor log x minus I pi tensor log x tensor log x. First term, I guess you can see, is the same as this one here, except that I need again to replace x by 1 over x. So this is delta 1, 1, 1, v3 of x. This one, I guess you don't need a lot of imagination. You see, it comes from 1 over 6, 1 over 3 factorial log cube x. And the third one comes from minus I pi log square x, and I should also divide by 2. There is a symmetry factor. So what do you learn? You learn that delta, let me just recap, v3 of 1 over x is the same as the delta 1, 1, 1 of v3 of x plus 1 over 6 log cube x minus I pi over 2 log square x. So previously what we said is, well, actually, this means that the arguments are constants up to something that vanishes, which was a zeta value. Here it's still a bit more complex because I had decomposed into 3. So these are, the kernel would be things that can be decomposed into 2, but not into 3. Those are objects of the type zeta 2 times a log. So what I can, for example, do is, let me, just to fix the idea, let me call this T. Let me expose things that have the shape zeta 2 times the log. Well, those are things that have weight 2 in the first entry, weight 1 in the second. So let me check if I should include such objects. So if the difference has them. Well, you have to go, well, let's go through it. So what you would get is the following. You would get E2 1 over x, cancel log 1 over x. That is what you get from here, sorry. That's what you get from here. Minus then you get lead 2 of x, cancel of x. That is this term. plus 1/2 log square x cancel log x. That is this term minus I pi log 2 log x cancel log x. That is the third term. Okay, so what can I do? Well, I can inject in here I know now what this guy is, right? We've looked at it here. So I can inject this formula. And well, we can see what it does. Let's go through it. So d2 of 1/x is minus d2 of x. And then what else does it have? Minus 1/2 log square x. X. And then there was plus I pi log x plus 2 zeta 2. Zeta 2 cancel log x. So the only thing that has happened here is that I've replaced d2 of 1/x by this. And here I should change sign because here I have log x, log 1/x. And then the rest, I just keep it as it is. So can we do this? Yes. Put it here. And so what happens? Well, you can see, for example, that this gives me here minus 2. So this term cancels this term. The same, this term will cancel this term. This term will cancel this term. So the only thing left is minus 2 zeta 2 tensor log x, which I guess you can easily figure it out, is the image of zeta 2 log x. So you have learned more. You have now learned that, well, the thing we started from, I remind you, on the previous page was d3 of 1/x minus my expression that I had found before. So what have you learned? Well, you've learned that d3 of x, d3 of 1/x should be this t minus 2 zeta 2 log x. And now, well, those were things that were decomposed into 2. So now the only thing that can be left is an integration constant, which can be zeta value or powers of pi. Now, constants, these constants you cannot get from zeta values in pi's, you cannot get from any other way than doing numerics. So the best you can do is to look at some integration boundary. So put x equal to 1. Then you get d3 of 1/x, that is zeta 3, equals t. T was here, and you can easily see when I put x equal to 1, the terms that have the log go away, and you just get zeta 3 again. minus 0 plus C1 zeta 3 plus C2 pi cube. So you can cancel these. And I must have C1 equals C2 equals 0. So you have found also the analytic continuation formula for E3 of 1 over x. So if x is, say, greater than 1, you replace it by the thing on the right-hand side. And on the right-hand side, all the functions have, for example, well-defined series expansion around the origin, and you can evaluate those.
One question here. So I think it's pretty well known that you can't write zeta 3 as some number times pi cubed.
Mm-hmm.
But is that a theorem? Would this prove that theorem, or is that
it's built in. It's built in here implicitly. You see, you're correct. I could, of course, say, but technically what it's shown is that this then should be 0, right?
Right.
Now, how should I phrase it? The way you do it mechanically is that there are codes that allow you to ask the following question. I give you a bunch of numbers, A1 to AM. Try to find integers and one, well, no, let me say it differently. It does not prove this. It's built in. That's why I can say C1 equals C2 equals 0. Why? Because if this was not 0, if you would find the C1 and C2 non-zero such that this was 0, so that zeta 3 would be proportional to pi cube, you would have essentially revolutionized mathematics. Then the whole mathematical structure that I've described would fall apart. It's something that is technically not proven. I think technically you don't even know if zeta 3 is transcendental. You know it's irrational as far as I remember. So here you get quickly into the realm of things that are also on the mathematical side just built on conjectures. You build conjectures and conjectures and conjectures when it comes to the numbers, okay?
Okay.
And the whole mathematical theory has these conjectures kind of built in as a starting point. So you assume that this implication holds. That different zeta values and well, all the odd zeta values are not proportional to powers of pi and so on. But yeah, that is a very good comment because it's very important. More questions? Okay. So since we have like 5 minutes left, I think it's not worth starting a new topic. You can go through another exercise if you like. You can look at exercise, and maybe just for the fun of it, let me show you how this works on a computer. And then we can also look at things that are a bit more sophisticated. So let's do the following. Just give me a second. So you should be able to see the Mathematica notebook now. There's a package that has all of this stuff implemented. for example, you can ask it, what is the delta, the co-product of a dialogue? And it would spit out what that quantity is. I could also ask it, for example, what is this? Okay. Can also just focus on, say, the terms that have logs, so objects of weight 1 in the first entry. And now here you see, for example, that log of, clearly log of 1 minus x squared, log of 1 minus x plus log of 1 plus x, right? That's clearly the case. And clearly log of x squared should be 2 times log x. And now I guess from here you can see that that, for example, is the same as this, except that I replaced x squared by x. So, for example, I can say, but let's go and say this is 2 times, recognizing the term that looks like 2 times the dialog of x. So now I have something left. What is the thing that is left? The thing that is left is the same as the first, as this, but with x squared replaced by minus x. Note that if I replace, well, as this, but x replaced by minus x. Note that if I replace log x by log minus x, nothing happens. That is the same because log x and log minus x differ by I pi. Log minus x is the same as log x, say minus I pi, depending on how I fix my branch. But if pi appears in the second factor, it goes away. I throw it away. Pi is only present ever in first factors. So I can also go and take this thing with minus x. And yeah, and then actually log minus x would be log x, say minus I pi. And so this should be an identity. So this should be equal to some number times zeta 2. But you can easily check if you put x equal to 0, that this holds. So this is an identity. So you can play with this and derive any kinds of identities you like. If you do it for other polylogs, so this would be like GA1, A2. These are more complicated. This would be a multiple polylog. The co-action will get, the co-product will get bigger and bigger. And so you see, this is not something that you easily do by hand anymore. So there you need really computers just to keep track of the combinatorics and of the terms. But all of these things are implemented, and you can easily manipulate these expressions and massage them pretty much into any way you like. For example, one question, let me stop, could be, imagine you have this function and you want to know, well, no, let's not go there. Another thing you can do is, what is a shuffle project of these things? So all of these things are readily implemented into Mathematica code. And you can use it for whatever manipulation of polylogs you want to use. The most useful function is usually the one that does the following. Imagine I want this, and I want to ask, okay, is there a way to get, or let's even do something else. I have this. Is there a way to write this thing in terms of functions that where the upper integration limit is a1? Could I do that? Can I find such a relation? You can automate the whole thing. I'm not going to, it's just to show off if you want. And I need to give the value some point at which I need to compute some initial condition. Remember, there's always this idea that some numbers, some boundary values come from initial condition. Let's just pick some point where we need initial condition. No, of course this doesn't. Why does it not work? Okay, show effect. I don't know why. Let's put in numbers. Yeah, sorry for that. Somehow, I don't know what's going on here. Yeah, let's do something else. Let's imagine you want to take this and ask, can I write it in this form? That you can definitely do. You would find this. This would be an identity. This multiple polylog is equal to this combination of multiple polylogs, where now always x appears at the end. You may ask, why do you want to do that? Well, that depends on the application you have in mind. But you can find identities and massage your results for your loops pretty much in any way you like, and all of these operations are automated. Okay, so I think this is a good place to stop for today. So today, just to recap, we've seen how to essentially work with polylogs, which is the kind of functions that you get for loops, how to use the co-product to derive identities, which is useful if you want to massage the expression, you want to rewrite it, you want to analytically continue your functions. And tomorrow we will look at how this, so this was more like at the application side, but tomorrow we will see how this whole structure is actually reflected in the amplitudes themselves. So far, we've only done mathematics. We just look at these functions. But now we can also ask, okay, if we now look at the functions that correspond to amplitudes, maybe there's more to be seen, and there will be more to be seen, but we'll do that tomorrow. Okay, good. Then if you have questions, feel free to ask. I want to remind you that today there's no discussion session in the afternoon. So if you have questions, you can ask now or tomorrow during the lecture.
I have a couple.
Okay.
The first one's trivial, the G0, 2. I thought you told us that G0, x was just log x.
Yeah, that's because the code has not coded like this, but this indeed is G0, 2 is log 2.
Oh, okay.
And the same, this guy would actually be 1/2 log squared 3.
Oh, okay. The other question I have is you, when you were deriving some identities earlier on, you would assume that x was between 0 and 1. Then you got an answer. Is that answer supposed to now work for all x?
In the example that I wrote down. So the identity that I derived, maybe let's go back to the notebook, to the lecture itself. Here we go. So you mean, for example, this relation here. That relation was derived under the assumption that, well, let's maybe go to the dialogue because it's more compact. It's easier to discuss it. So for the dialogue, we had this identity here, and we said it was derived under these assumptions. Now, the question is, what does it mean the identity holds? And here you see the question. Imagine I were now to say, well, what does this identity become for x negative? Right? X not between 0 and 1, what does it become for x negative? I would need to tell you what is log x for x negative. Okay, I can of course take this identity and analytically continue it now to x negative, but of course then my log x would spit out additional i's.
But didn't you already define what log x minus x was below?
Oh yeah, of course. If I use this, then of course I can plug this into the expression above and derive from there what it would be for x negative. Yes, as long as I'm consistent, I can always take whatever identity I've derived in one region of parameter space and continue it to another.
Mm-hmm.
But the only point I want to make is that if you just plug in x equals -2 in that equation above, be careful. You have to interpret log of -2 in that case as coming from the same transcription as what you had here.
Right. Okay. And my last question is, in this literature, you often see the term symbols.
Yeah.
Is that something that we've already done, but you haven't used that word, or is that coming?
I haven't used the word. So maybe we have it here. Go there. Yeah, maybe let's do that because it takes 5 minutes and then you see the connection. And so it's maybe good to finish the lecture. So symbols. We've seen this, the Hopf algebra, it allows me to decompose things into lower weights. So for example, the dialogue, we've seen the example many times, this has weight 2. there are these two trivial terms, which have weight 0 in the first entry here, weight 2 in the second, or weight 2 in the first, weight 0 in the second, okay? And then there was this term left over, which was the only non-trivial one, where everything was decomposed into weight 1 objects. This guy is a symbol. It's like the maximal decomposition, where you decomposed it, every object of higher weights into its building blocks, which are weight 1 objects. So for example, for the trilog, you have a decomposition of the weight 3 object into weight 3 and weight 0, weight 0 and weight 3, weight 2 and weight 1, weight 1 and weight 2. But then the weight 2 objects, I can decompose again further. And remember, there was this co-associativity property which tells me that whatever way I iterate, the decomposition doesn't matter. I always end up with the same result. So if I iterate this decomposition of start from the weight 3, this is the decomposition we did. I can iterate the decomposition, for example, start from 1 weight 2 and decompose it into 2 weight 1s, so I get a triplet of weight 1s. Or I could have done that from the other direction. It doesn't matter, I get the same answer. So this maximal decomposition is a unique thing. Whatever way I do it, I end up with the same thing, and that is the symbol. I do the same for weight 4. Let's not go through it. So that is the symbol. The symbol is just the maximal decomposition of the function into, so of a weight n object into n weight 1 objects. And that decomposition is unique and called the symbol. And often this is, so the symbol of the log is itself. The symbol of the dialogue is the thing that we've seen many times, and then you can now work out what it is for other objects. What people often do in the literature, since you see everything is decomposed into weight 1 objects which are logs, you just don't write the log. So instead of writing log 1 minus x log x, you just write 1 minus xx. And it's implicit that these things are logs. But that is the symbol. It's part of what we've done and what we've seen. It was implicit in what we've done.
Okay, thanks.
More questions? Good. There are no other questions, and I guess we can end the lecture today. Remember, there's no discussion session today, but we continue then with the last lecture tomorrow morning at 10. See you tomorrow then.